Okay, on deck for today is 7.3, which is trigonometric integrals. Okay, so these are not to be confused with inverse trig integrals, which we've already done, those transcendental functions. But what they are the true trigs. So we're talking about sine, cosine, in particular sine and cosine, but also tangent, secant, and much to a lower degree, cotangent and cosecant. What we're really going to focus on today is sine and cosine. And we like those, and those kind of get their own special chapter because of the relationship between the integral and the derivative. The derivative of sine is cosine, and the derivative of cosine is negative sine, and then the integrals follow suit. So that relationship makes for some kind of unique integrals that warrant really their own unit. Before I can get into this, one thing we really need to talk about is the various trig identities. So we need to remember some trig identities. And ironically, I was just talking to Miss Williams, who teaches the pre-cal, and she was saying that they were going through this in her pre-cal class, and that traditionally this has been one of her weakest testing periods where students tend to do the worst. I said that's too bad, because this is really an area that when students don't understand their trig identities, it really shows up in this unit, because they have to use a set number of them proficiently to be able to manipulate the integrals into something that they can actually integrate. So these trig identities are going to come back. Now, thankfully, I noticed your sheets from pre-cal were like 4 or 5 or 6 pages long. I couldn't even remember. I was actually helping a pre-cal student with one of the identities. But in hindsight, you don't really need all those. The ones that you need are the double angle identities. And the other one that you need is the Pythagorean identity. It's called Pythag, that being sine squared plus cosine squared of x equals 1. So this is the main idea, or these are the main ideas that we really need for this unit. So that's where I'm going to start. I'm actually going to start with a little bit of a pre-cal SL review depending on what you took. And we're going to start at Pythagorean identity, because all good things actually come from there. So if we have sine squared plus cosine equals 1, then from that you can also say that cosine squared of x equals 1 minus sine squared of x, and that sine squared of x equals 1 minus cosine squared of x. That's the easy step. But if you divide your sine by sine squared of x, so you're dividing this side by sine squared of x, this by sine squared, and this by sine squared, then you will also get a really interesting identity of 1 plus cosine divided by sine is cotangent squared of x equals 1 divided by sine squared of x is actually cosecant squared of x. And then likewise, cotangent squared of x equals cosecant squared of x minus 1. And again, we can divide now by cosine squared of x, which will give us tangent squared of x plus 1 equals secant squared of x, which means that tangent squared of x equals secant squared of x minus 1. So these Pythagorean identities, particularly the ones with cosine and sine, and the ones with secant and tangent, in particular, these guys are going to come up a lot in today's discussion. Not as much the cotangent cosecant. So then on top of these guys, we also need to discuss the double angle identities. So we have that sine of 2x equals 2 sine of x cosine of x, and that we know cosine of 2x equals cosine squared of x minus sine squared of x. And from that double cosine angle, what you can do is you can manipulate this guy such that cosine squared of x equals cosine 2x plus the sine squared of x. So you can bring that sine squared of x over here. So that means we have cosine 2x plus sine squared of x equals cosine squared of x. And adjusted further, if you change that sine squared of x to be 1 minus cosine squared of x. And then if you change the sine squared of x, it's going to be cosine of 2x plus 1 minus cosine, I almost wrote sine, cosine squared of x equals cosine squared of x. So if I add that cosine squared of x to one side, I'm going to get 2 cosine squareds of x right here. Bring that over. I'm going to get cosine of 2x plus 1. If I divide by 2, I'm going to get 1/2 cosine of 2x plus 1 equals cosine squared of x. And then likewise, I can also make a similar assertion about sine. It's going to flip the sign though, no pun intended. Sine squared of x equals 1/2 1 minus cosine of 2 of x. And that's where they get the idea that double cosine angle there, cosine 2 of x, if you have that, multiply out that 1/2, you get an interesting ratio with 1/2 there. So we have these guys as well. Let me highlight them right there, right there. These are the other identities that we're really going to need today. So this would be a good time if you don't have this out or you want to keep these handy. I would get out your little reference sheet because that will help you kind of navigate through some of these identities. And as you pause the video, you can say, oh, which identity should I use? I would star these identities. I think we've already highlighted them, but I would definitely star these identities as important because these are ones that you're going to have to come back to solve a lot of these integrals. Okay? So let's talk about how we utilize these to integrate. So when we have trig integrals, you have to think about what methods you're going to use to solve. The first method, a method that we've already widely used, is known tools. So that would be things like substitution by parts. And then substitution by parts, or maybe some kind of formula, an antiderivative. Not necessarily the reduction formula, because the second option you might have is the reduction formula. So the reduction formula is the second option you have. And we don't have very many reduction formulas in our tool belt yet, but we will by the end of the day have another one. So that reduction formula is another option. And then the third option that you have is to modify using identities. And then from there, do 2 or 1 after you do 3. So we specifically modify in such a way that will allow us to solve a simpler integral. And that's where these trig identities come in handy, is how can we change this trig piece to be something that is more friendly to work with. So that's where we're going to start, is number 3, because we've already done a lot of practice with number 1, with things that didn't need to be modified. And the reduction formula is going to come from our kind of synthesis of other integrals. So we really need to start at number 3, modify using identities. Okay, so when we're talking about trig integrals, we're talking about integrals beyond the realm